Pascal's law is the basis for the hydraulic principles that are used in automotive brake systems. Pascal's law states that pressure applied to an enclosed fluid is transmitted with equal force throughout the container. The first principle of brake hydraulics is a principle of fluid dynamics that states that unlike air or gases, fluids cannot be compressed. Take an automobile engine as an example. When the intake valve opens on the intake stroke, the fuel-air mixture is pulled into the cylinder. The intake valve then closes on the compression stroke and the mixture is compressed as the piston moves upward. If we were to fill the cylinder with water during the intake stroke and close the intake valve, the piston would be unable to move upward because fluids cannot be compressed. Simply, the engine would stall. The second hydraulic principle is that fluids can transmit movement. If you have two cylinders that are connected with a pipe, and the cylinders and pipe are filled with fluid, any motion applied to one cylinder to force the fluid down will be transmitted to the other cylinder to force the fluid level up. In a brake system, the movement or motion of the master cylinder piston is transmitted through the brake fluid in the brake lines to the wheel cylinders or disc brake caliper, causing the wheel cylinder or caliper pistons to move outward. The third hydraulic principle is that fluids can be used to apply pressure to transmit and increase force. The amount of force that is generated is proportionate to the amount of surface area that the force is applied against. Pressure is equal to the force applied divided by the surface area. The pressure of a liquid in a closed system is the force exerted against the inner surfaces of the cylinders, valves, and hoses throughout the system, and is measured in pounds per square inch or psi. Pressure applied to an input piston surface will be transmitted as force and be the same at an output piston that has the same diameter as the input piston. If the input piston surface area is smaller than the output surface piston area, the force exerted by the output piston will be greater than the input force. If 200 pounds of force is applied to an input piston with a surface area of 10 square inches, the resulting pressure will be 200 divided by 10, or 20 psi. If that force is directed to an output piston with a surface area of 25 square inches, the force will be 500 pounds. But if we increase the size of the output piston to 50 square inches, the force will be multiplied to 1,000 pounds. Pressure, therefore, is inversely related to piston area. The smaller the input piston, the greater the pressure that is developed. Similarly, the greater the output piston area, the more the resulting output force is multiplied as the output force equals pressure times surface area. As with a lever, the distance of piston travel is also a consideration when pistons of different sizes are used to transmit force. If a 10-inch input piston moves 2 inches as it applies 50 psi to a 100 square inch output piston, that output piston will only move 0.2 inches as it applies 5,000 pounds of output force. While it can be calculated mathematically, trust the rule that says if an output piston is larger, it will transmit more force and move less than a piston that is the same size as the input piston. To see these principles in action, look at a wheel cylinder on a drum brake system. The pistons on the wheel cylinder only move a fraction of an inch compared to the movement of the piston in the master cylinder. Yet they apply hundreds of pounds of force to the brake shoes to force them against the drums to slow the vehicle.